Okay, so while everybody's getting set up, sorry, Joe. So this is a panel discussion. This is an opportunity both for our speakers and members in the audience, both here and if you're viewing on the webcast, you're able to submit questions to try to draw out in more detail some of the issues that brought up by the speakers that the speakers this afternoon will address, which are a lot more about testing and some physical sensor issues. That either things are in more detail or maybe points in which you're sure there's not a single standard answer. That's what we're hoping, and that this panel discussion will let us sort of begin to set the stage of the major factors that we're going to consider during the scrimmage tomorrow, and also include in the report that we're hoping will provide some overview or some idea of really what are the next steps or what's the major considerations as we start thinking about manufacturing nanosensors. So that being said, I'm going to hand it to Joe, who's going to moderate the panel, and I think he has some questions to begin.
Thanks to our group here, we have some really good questions to start out. And one of the things, question one addresses a supply chain and supplies of nanomaterials. And believe me, this is basic to using any nanomaterials in a product. Of course, the process can be chosen, and the process needs to be repeatable, and we work on quality, and we work on throughput, and we work on yield for different processes. But if you don't have a good source of supply for the nanomaterials, and my story is I started using Helix single-wall carbon nanotubes to make the ozone sensors that we finally took to market, and last year they stopped answering their phone. and I thought, what? So we had to qualify another material, and that's not easy. We bought nanotubes from 3 or 4 different suppliers. We finally wound up with US Nano. We had to buy 3 batches from them, and all 3 batches came in different. They were different processing, different hydrophobicity, so we had to change the ink formula. They had different bulk densities, so the loading was different for the same amount of material. And so these kind of difficulties plague not only startups, but even a large company who would want to use these materials. And so the first question has to do for the group, if you could address the supply chain, how to choose and source nanomaterials, especially with respect to integrating them into your or any fabrication process. So who would like to start?
I have very similar stories. Not just nanotubes, but nanoparticles also. We had a company, I'm not going to mention company names, but lately we have used zinc selenide particles, and the first batch was really nice, you know, nanoscale, 10 nanometers or less. Next batch was 200 nanometers or more, and we're trying to use these particles to build 50 nanometer structures. So it doesn't work. That's right, yeah. So it took them a long time. It took them 6 months actually to get back to the supply that we wanted. With nanotubes, I mean, we had some companies giving us semiconducting nanotubes. What we thought was semiconducting nanotubes. They were multi-wall, and were not semiconducting. And we fought with them, and they would say no. And so we had to do Raman, we had to do TEM and SEM, and we have to build a device to show them that it was not semiconducting. So you run into this all the time, and the best protection is to have very clear spec when you buy something, and you can tell them right up front if it does not meet these specs, which is actually also your advertised specs, right? That's yeah. We're going to return it, you know, and go for somewhere else. And it's better to have an alternate, you know, not just depend on one source, because like you said, you know, overnight they can disappear, and then you have to start over, and it's very expensive to qualify something different.
Right. Anyone else? Yeah. Sure.
I forgot to introduce the afternoon speakers, so if you could introduce yourself. Sure. I'm sorry.
Oh, maybe Susan first?
No, you're going to answer.
Okay. Yeah, my name is Abhishek Motayed. I'm founder and CEO of N5 Sensors. Just a brief one-line intro to our company. We make microscale gas sensors on a chip, like single chip sensors. I guess that's pretty much it. So, yeah, so the answer, I mean, to this question, supply chain management, it's actually so important that it can almost make or break your company, especially as a startup. If you first time you're trying to do this, and you have to keep this in mind that at the end of the day, If you're lucky enough to establish your own manufacturing facility, that's great. But for most of us, it's incredibly challenging. So that means you'll be looking for a contract manufacturer, maybe somewhere in the US, somewhere outside, who knows. But then doing that, you also have to ensure that the manufacturer that you are trying to work with, they will be okay handling the materials that you are introducing into your process. So for example, the product that we manufacture, inside we put like about 35, 40 different processes on top of each other to deliver the final product. But starting material is a wafer that we get from an epitaxial vendor in Europe. And then in between, you have chemicals, you have targets ordered from different companies, different vendors. You can list, like, there's a huge Excel sheet with hundreds and hundreds of line items go in, and you're trying to control every single aspect of that process line, we call it, from wafer specs, including RMS thickness and whatnot. So, and then at the end of the day, you have to understand that you have to take all of that, because if you want to scale your company and make some money out of it, that's the whole point for people that are trying to start a company and build it. So you have to transfer all of that into a commercial manufacturing facility. And most of the times, they don't want to deviate from what they have been doing for the last 10 years. So that has been a significant challenge for us. They said, no, we can't do, or we can't put this material in one of our tools because this is our main business line. And that, you better know this, now than a year later when you have invested about $1 million transitioning the manufacturing to the contract manufacturer. And they said, no, we can't do that. So my advice, and learn hard way, is that you have to talk to all these contract manufacturers and the vendors and figure out what is compatible down the road, because it's not now, it's not today, but you're looking at future once you have a product, like in your scaling up. So it's start early and just basically qualify everything that can go into production and will go into production and compatible with the tool chains, and you ensure the vendors are going to be around when you want them to scale up. So it's challenging.
So this is my bad. We didn't introduce the panel. So why don't you pass the microphone? Let everyone introduce themselves and where they're from, and we'll just pass the microphone.
Sounds good. I'm Sameh Dardona. I am a principal research scientist at United Technology Research Center in East Harvard, Connecticut. We are doing a lot of work in aerospace and building industries application, and I will describe that in the afternoon session.
Okay, so I'm May. I'm the assistant professor from Kansas State University, actually, and startup company as well with my postdoc. And we try to focus on the nanoparticles, and we hope to have this more porous, more specific particles that can integrate with the sensor part. So we try to have the added value to the particle to form the integrated system. So that's really starting the company as a first step now.
My name is Ahmed Busnaina. I'm the director of the NSF Nanoscale Science and Engineering Center at Northeastern University.
I'm Susan Rose-Pehrsson. I'm the director of the Navy Technology Center for Safety and Survivability, and my expertise is in sensor arrays and multivariate data analysis and sensor testing.
I'm Joe Stetter, and I'm currently with SPEC Sensors and KWJ Engineering in California. And that's a perfect lead into our next question, which is about making multiple measurements, which you can make through multiple sensors or using a single sensor in multiple conditions of measurement to improve the quality of data, both in terms of multivariate data analysis, or I probably formatted to get more data that's suitable for multivariate analysis, which can pull out information from your data, and how to overcome variability in measurements and in sensors stability over time and temperature and other things. And the perfect person next to me, I'll go back this way, as Susan can address multivariates and sensors.
Sensor array data is very difficult, as you know, and it dates back to many years ago. How do we handle this? How do you design a sensor array? And we've been struggling with this for decades. Recent papers have been on the limit of recognition as opposed to the limit of detection or the limit of quantitation, because when you're dealing with multivariate, first you have to have the pattern, and the pattern may change with concentration. The other issue is I've always believed that it's a good idea to put multimodal sensors together so that the information that you're getting is varied, that you're measuring different parameters about that chemical and not just similar parameters as you would have if you did an array of just one type of sensor. And so, but that introduces its own challenges. How do you data fuse information that is coming from multiple sources? Because many times they have different response times. They have varying parameters. And Joe and I had this experience many years ago when we were looking at some electrochemical sensors, and some sensors would dominate the entire pattern. So then we had to do pattern normalization before we could even identify the chemical to move forward. Some research that's going on in my group at the Naval Research Laboratory is in design theory. And we're trying to take information theory and apply it to sensors. And some of the first information that's coming out of that is more is not always better. You can put a lot of sensors together, and in some cases, all you do is increase the level of false alarms. And so you're not actually getting additional recognition. So you have to do this in a very intelligent way. And many times your sensor array is no better than the weakest sensor in the array, depending on how you do your algorithm development. So as you increase the number of sensors, this can be a very complex approach to sensors, and the whole field of statistics and so forth has to be expanded from the univariate measurements to the multivariate measurements.
I want to say one thing that Susan taught me in the mid-1980s. When I was doing this work, I was a scientist, and she was working with Peter Jers at Penn State doing, at that time, this is very new stuff to do multivariates and pattern recognition and principal component analysis and these kinds of things for data sets. And the one thing that struck me as important, which I've never forgot, was in order to do pattern recognition, you can get that from any group of sensors or sensory signals, operating them differently or whatever. But if you do that for a series of chemicals in a certain matrix, that's your data set. If you then take an unknown and you do it in the atmosphere in a different matrix, that pattern is not a member of that data set mathematically. And it's incorrect in terms of rigorous mathematics to assume to interpret that pattern with that principal component analysis. So you either have to do principal component analysis or multivariates for every conceivable data set in every conceivable environment, or you have to be stuck with some imperfect analysis. Now, having said that, all analyses chemical analyses are imperfect. Even atomic absorption, which has the finest of lines, and you can do a nickel analysis and you have one line that you can pull out of the AA spectrum. If there's an interferent in there that produces that line, you then will get an incorrect, a non-valid, I mentioned the third part, accuracy, precision, and validity. You'll get an invalid measurement even from an atomic absorption measurement. The question is, how probable is that? And the answer is very improbable. That's a pretty specific line. in the world of chemistry, which is extremely diverse. So constructing the multivariate data set to be probabilistic of any application data set is, I think, the biggest challenge that people have. And the second challenge is if you have multidimensional sensors, a heterogeneous array is better than a homogeneous one, typically for information content. But if you have all of these sensors and they all have drift in n dimensions, how do you correct for this drift and compensate or calibrate? So the people that say AI is the answer may be right, but I don't think it's going to be simple.
There's another application that nanotechnology introduces to this whole field of sensing, and that's the ability to go from zero-order measurements to first-order and then second-order. By the time you get to third-order measurements, then you can introduce that unknown, and you don't have to have all the testing that is required if you're working in zero-order or first-order, because and the examples of that in the laboratory are things like a GC mass spec, because now you've got the resolving power of the GC in addition to the mass spectrometer that's already giving you multi-information, and then you go and say, or GC mass spec, mass spec. That's an example of a third-order instrument. Well, we can start to do that now with nanotechnology because we can put one type of separation device that may be very fast and very small in front of another type of sensor. And so we can start to think about developing field applications of third-order sensory devices that can handle real-world unknowns.
The only thing I say about that is that everybody wants, you know, an array of sensors that does 100 chemicals or something. DHS wants those. Companies want that. So everyone you deal with actually wants these sensors. They think it's very easy. You just plug them in and they work. The one thing that we deal with, but you talked about it a little bit, is that sensor-sensor interaction. You know. So we talked about some higher requires low voltage, the other one requires higher voltage, some electrochemicals, some chemi-resistive, and so forth. And if you put all those in the same array, you will have noise, you will have some maybe thermal effect, maybe electrical effect, and those can lead to a lot of errors, basically.
Could you say something about the molecular diversity in biology?
Oh, yeah, sure. So that's actually my interest part for the biosensors, and totally agree with the multidimensional integration. So for the sensor we're talking right now, it's not just a sensor itself. Actually, it's an integrative sensor device. So it's not just the material, it's really the device fabrication combined with the material surface chemistry, and then meanwhile with electronic integration readout. So it's a whole system. So I think it's a great point that we can integrate the sampling process and combine with just the material sensing part, because that sampling integration can really give you the much purer sample you can target to. And especially for the biological sample that we're doing, the biosensors, we always want to integrate the sample preparation in just the integrate with the sensing part. So this really can purify the biological samples. Mostly they are really complex matrix, and for example, the water or the foods, and they are really complex, the matrix, and we integrate this sampling process, we can just purify the target we want to sense. And in that case, we have the much better improved specificity and the sensitivity, and that actually can solve the problem for the radar drifting and also the precision problem as well. Mm-hmm.
So, Sameh, from United Technologies, from industry, maybe you could start us off on our third question, which is very important, of integrating these for real-world activities. It says, can we detail what are some of the needed standards in materials, processes, terminology, and things that would be useful for integrating them. My small experience with United Technologies research is that they have a group there that's interested in sensors like for environment and integrating into architecture. So it's part of the infrastructure and the architecture, along with carrier conditioning the air and things like that. But how do we interface some of the new nanotechnology materials and processes and terminology? What standards and what kind of standards would help get us to products faster?
Very good. So I would like to say that we have two applications within UTC. One of them is the aerospace application, and one of them is the building management application. So in the building management industry, what we deliver to residential buildings are smoke alarms and flame and fire detectors. And a lot of what we do right now is kind of based on ionizing the air, and then you measure a current as a baseline, and then, for example, when you have a smoke, the smoke will reduce the amount of current you detect, and therefore you would know that there's a smoke in your way and so on. So what would work for us is to detect, for example, all kinds of smokes. When you have a kind of a smoke coming from kind of material that's made out of wood or plastic, and you will have different particle sizes. And then right now we are looking for nanotechnology as a way to enable small false alarms in smoke detection. And the way we do that is that we look into materials that could be printed, that could be kind of made into conformal and into flexible substrates. And this material could be used as ion sources or as electron sources. And then the standard we look for is more like, if I want to have nano ionizers, if I want to have a material that can create ions or create electrons as a source for my ionization, I want to have some requirements on the material in terms of lifetime, in terms of amount of currents can handle without having any dual heating effects in it or degradation from the amount of current we pass into it. I want to have kind of requirements on the stability of this nanomaterial in ambient conditions, or if there is kind of oxygen that could surround the material during the operation. Would that oxygen destroy the nanomaterial, or it will still function as supposed to be?
By the way, what you're saying, and the audience should recognize, is very typical of industrial needs.
Yep.
He didn't say a lot about the sensitivity or the silicon.
Yep.
He's assuming that it's going to do that.
Correct.
He said the lifetime and the reliability.
Yep. So
because without that, you cannot market a product for people.
Absolutely. So in terms of nanomaterials, our research center has been exploring nanomaterials for those applications. And as Joe said, one major barrier is the lifetime, because nanomaterials are small and they have different properties in terms of heating effects, in terms of melting effect, and so on. A lot of times we drive some voltage and current through them, and we look into them after a few weeks of testing and so on. We find degradation, we find some chemistry being activated within the material, and that's because of some of the impurities and some of the polymers that are part of the formulations. So the quality of the samples are critical. The lifetime in operation environment is also critical for our application and being able to deploy it and meet the requirements of 10 years of operation, because right now we have smoke alarms that can live 10 years in your house based on radioactive materials. And we are looking into green. We are looking into green technology. We're looking to replace those radioactive materials with nano-based ionizers, for example. And the requirements will be the same. The requirement is going to be 10 years of lifetime. And that's where we need some sort of improvement in the nanomaterial formulations and in the purity of those samples.
So we have time for one last comment if someone wants to summarize the panel or say something unique. Anybody?
Well, actually, you said you have time for one more question.
There we go.
So, well, actually, I do want to follow up on the question about standards. And so, and it kind of came up in some of the talks. Like you're saying, Sameh, that you have particular things that UTC wants to see. And is this an issue, do you think, for some sensor developers, where you've got this technology, you made it in your lab? To what extent do you think most developers, especially early on, actually know the standards that their material needs to meet? Like, do they understand the conditions in which it will be used? And is that a big failing point, do you think? Like, when you talk in academic research about licensing that technology, do you find, I didn't know it had to last 10 years? I mean, is this an issue that really, it relates to testing in a way? People don't understand the environment in which the sensor will really be used, so they have to test. And so a little bit, if maybe May and Ahmed could speak to developing in the lab, how aware are you of these issues? And if maybe some of the people who try to license could see, is that really a big issue? Because again, part of the purpose we hope for this panel is to educate the early stage developers. So certainly I'd appreciate any comments people had on that.
Okay, of course. Yes, but you have to explore and invent in the lab. But then, of course, when you get to the practical side, you have to start considering other things. So it's best to be aware of everything. But maybe the panel has a good comment.
I'll just mention one example. So basically, like what Sameh said, is that they assume that, like Joe said, they assume that you will deliver, but then they want the lifetime, and they want reliability. But for example, when we did an Air Force project, for example, they gave us 2 pages of specs, including the lifetime, including the sensitivity, including the power requirement, including all of that. So sometimes actually you have a list. Now whether you can meet that list or not, that's a different story. But you do have a list. And companies actually, they don't give you that specific list usually. They assume you know what you're doing. And they only care about the big stuff, but then when you deliver something that does not meet their specs, they'll let you know. So actually having specs like that is very, very important and very, very helpful, because it helps the researchers, for example, try to meet that. And if they're lacking in one of these specs could be 2 pages, then they try to modify and adjust. For our case, for example, one of the specs actually was not even the spec that I talked about, which is the signal strength was not even on the sheet, because I don't think they got to that point yet, but we ran into it. I said, well, nanoamp, I mean, initially our sensor was only like picoamps, and you have to have a shielded room to even get that signal, so you couldn't do it. I said, well, this is ridiculous, you can't have that, you have to redesign your sensor completely. And then they got to 10 nanoamps. I said, no, that's not good enough, you have to go to milliamps. And then they redesigned the sensor several times until they got to that point. So actually having specs either from companies or government agencies is very, very useful, I think.
Yeah. But like maybe you feel that you have them, so they're definitely very useful, but when you're developing, a biosensor, do you feel that you have that, and how can you get it if not?
Yeah, to be honest, at the first point, actually, we didn't really to get that information. So from the laboratory, we really have that experiment discovery to validate like SEM and TEM, some like we established in the lab standards cannot to validate the material we discover, we fabricate. And once we feel that's the validate from our standing points, and then we move forward, actually that would be really useful information. We cannot align our protocol with the standard protocol. Mm-hmm.
I think another area that is frequently overlooked by sensor developers is sampling. And I think sampling can make or break the performance of a sensor.
Indeed. Indeed. Any questions from the group before we break for lunch?
Yeah, because we did put off the questions from before as well. So if anybody has any questions from before or final comments to raise.
Yes.
Yeah, I'm Mark Chappell from the Army. You mentioned about the multivariate analysis. In particular, challenges. Okay. I heard comments about multivariate analysis and trying to use that in a sense to capture the formulated properties of the sensor itself. But you're limited to the fact that your data, your multivariate analysis and the structure that evolves from that is only based upon the data that you have, and you don't have any confidence necessarily you can extrapolate that to other material types unless you have appropriate calibration data. So how do you propose to overcome that? If you apply like a machine learning or deep learning, the system does the prediction classifiers for you, and you don't know if those are right or not. You don't know what they mean. You don't know how they articulate into other. So how do you propose, or what do you see in terms of approaches to try to address the issues? Given you're dealing with a formulated material, it's one thing to look at the raw material properties themselves, but then the formulation itself endows it with a whole different set of properties sometimes. How do you bridge, what's the view in terms of how you bridge that gap?
Okay, so before I defer to Susan for this, I'll give you one example of a very successful multivariate analysis. It was the degradation of olive oil. And the experiment was done, they took a bunch of olive oils, different grades from Italy and from Greece, and they measured the degradation and with a mass spec. And they found out that the molecular basis for this was formation of nonaldehyde, okay? Then they took olive oils, they spiked them with nonaldehyde, all the different olive oils, and they did multivariate analysis, chemical sensors sniffing this nonaldehyde spiked samples at different concentrations, and they created a calibration curve. And then they went back and validated that and took olive oils and let them spoil, and they fell exactly on the multivariate calibration curve. That one, they understood the molecular basis, they understood the matrix, the samples were from the same matrix, or virtually the same matrix, although there is biodiversity from year to year in olive oils. It was sufficient to show that this multivariate analysis technique worked for spoiling of olive oil. Now, that's a good model or an example of a successful one. But you can see it's quite limited when you think about that in terms of, you know, ambient air or something, or breath, for example, with thousands of chemicals. And Susan, maybe you have a more detailed comment.
That's a perfect example of where electronic noses have been successful, because those are very controlled experiments where we can control the environment in which the sensor is working. That's a closed environment. Where sensor arrays frequently run into problems is in the open world environment. And that's where you can't predict every interferent that they may run across, and we don't have enough money in the world to test for every variation that they may encounter. That's where we need to rely on nanotechnology to help us get beyond zero order or first order sensors and move into second and third order, so that we have that more robust approach. That's one approach. The other is sampling. Many times sampling can limit the environment in which your sensor has to work, and that's a very powerful tool as well. A prime example of that is the IMS. An IMS is an instrument that can be used in ambient air. Well, it doesn't like water. Many of the chemicals that it's trying to detect when it clusters with water gives a different retention time, and so you miss the detection of it. Well, if you can limit the sampling such that you can reduce the water, and they do that by circulating dry air within the instrument, then you end up with a very powerful tool. So those are two approaches that I would think. That's also the reason why we're looking at this design theory as a way of overcoming some of these open world problems.
Thank you. One more?
I would like to mention that from our experience, one way to address the issue of multivariant is to use multiple technologies. So basically, when you think about a sensor, sometimes you think about one technology or one way of detecting something. Like, think about a flame. If I want to detect a flame or a fire in a room, the flame has signatures in the visible, in the IR, and the UV bands, right? And if you stick with one technology, for example, a UV detector, you can design one for and print one for probably less than $1, right? But that UV detector could have also response to the sun radiation, right? And then you would think that you can measure fire when you are measuring the sun radiation itself. Therefore, one way to do it is to integrate another technology on the same platform. So which means you can add IR detector, right? And then you can go even further and add different technology to the same platform. So a platform that can integrate more than one sensing technology, not only the electronic nodes, but also think about using optical in addition to semiconductor, in addition to, for example, resistive, in addition to radar or RF technologies in the same platform. And you have different ways of measuring the same thing. And you have validation here, therefore, from multiple detection mechanisms, and that improves the false alarm and makes your component more robust in the environment or the application. So we do that a lot in the aerospace and in the building management technologies, where we integrate more than one technology for the same sensing principle.
More questions?
You probably won't be able to answer this, but I'm asking anyways. I'm Angela Irvin. I'm a program manager at DHS Science and Technology. And so a lot of our customers, which are the DHS components, Coast Guard, TSA, et cetera, they don't really know what their requirements or needs are. So they do come to us, and I think somebody mentioned wanting everything for no cost, no false alarms. Yes, we get a list that looks just like that. So throughout the talks, you know, I heard things: sensitivity, regeneration, repeatability. If you had to kind of prioritize those characteristics, would you be able to do that? How would you do it? What should we be thinking about, we being the program managers that are deciding how to spend dollars to fulfill the needs of our customers? How do we, you know, think about these sensors and how to prioritize so we can get some kind of product out in the field?
So I'll ask the panel to chime in on this. But from my point of view, I would like to see agencies write performance specifications rather than characteristics of a sensor. So for example, I'm a fireman and I want to run into a building and I need to know whether I need my self-containing breathing suit. A requirement for an activity. I need to inspect train car derailments and chlorine is often spilled. I got to have a simple chlorine device somewhere on my equipment, and I carry, you know, a rifle, a gun, and a scuba system. So I would rather see agencies write those kinds of user scenarios and then ask the community to say, let's define some sensors that approach that or could maybe in some way combine and get a useful tool to that person so their health is protected or asset is protected or something like that.
In my experience, I believe sensor-to-sensor reproducibility is very, very crucial, because you can't afford to do all the testing that needs to be done on every single sensor that's produced. You have to be able to do the testing and then hope that that calibration transfer moves to every sensor in that batch, so that all you're doing at that point is validation testing.
Yeah, I think Joe said what I was going to say. Basically, it has to take the user and the sensor maker to actually come. If the user doesn't know, then they have to get together and actually decide what are the specifications, because only the user will know the needs are, you know, and the sensor designer or the sensor manufacturer will know what the limitations are, and so they can reach some compromise. For example, we run into a lot of people that ask for a sensor that we cannot make, for example, you know, and so but they may actually have some kind of flexibility in terms of knowing, yes, well, I really would want, you know, 500 degrees Celsius, but I can live with 300, you know, say, okay, then we have something, you know. So, but like a TSA or a situation fire or chemical spills and so forth, only the people that actually deal with this will know what they want, what they need. And then the user can say, well, okay, this sensor that I can give you will last for 6 months. They say, no, that's no good. I mean, I want it for like 5 years. I say, well, you know, maybe we can do it for 5 years, but we don't know yet. So for the Air Force, for example, with our project, they gave us a very long set of specification. But then in our development, we found out other specification that was not there. And because they didn't actually know, because they didn't have any sensors at that time. They were actually funding a new type of sensors. So I think what Joe, you got it right on the money, because it's very important.
So you prompted me to say science and technology is a human endeavor, and it's very evolutionary. It's a human endeavor, and it's very evolutionary. And to have the user define on a regular basis what their needs are in terms of fit, form, and function, and then to have sensor people describe what they can produce. So maybe 300 degrees C fits 90% of the market. You could do a lot of good. You might still want to do that, even though when you get the requirement from the user, he says that he needs 500, which covers all of his situations. But maybe 300 covers 90%, and that would be a tremendous advance. And so you get together and you decide what's critical. On the other side, United Technologies knows if they don't have a 10-year sensor, they're not competitive in the market, and it will never go anywhere. And so that's a drop-dead requirements. And so you have drop-dead requirements, you have nice to have, you have want to have, and that dialogue must go on between the user and the sensor developer. And I always try not to draw hard and fast lines.
Okay, so I think that the different way to think about that question is we can start with the problem identification. So usually you don't know how to connect what type of user with what type of sensor develop, but you can start with the problem identification. That's really the problem and present in the real world, and we need to solve this problem specifically. And that can bring you to specific user and developer together to think about a solution, to come up with a solution to solve this problem. So that can be more efficiently to facilitate this communication and to develop the sensor that can be used in the real world.
Yeah, I'll comment from our experience as a small company trying to develop a product. So, as reflecting on Joe's comment, and everybody said the same thing. How you develop what's important to have and what's needed is basically you dialogue. So the way we do it is, and one thing is, every sensor application and customer is different in terms of needs and requirements. Like I said, one would be 60 degrees C is okay. The other person, it's 90 degrees C is not nearly enough. So first step is sitting down, together face to face and sort of discussing what's needed and then what we can do. And other thing is, it's eventually at the end of the day, as a manufacturer, as a business, running the company, you have to make a decision whether you actually want to pursue down that business line to address those markets, because sometimes specifications are very market oriented and the application, like automotive sensors have very different specifications versus your smart home sensors. And then if you're trying to address a wearable markets that we saw on the slides, packaging requirements are, out of this world. Because guess what? You don't care. You don't use your cell phone for 10 years. You'll be lucky if you use it for 1 year. So lifetime is important, but guess what's more important? The packaging size, form factor. You sit down with those people that makes these smartphones, when they talk about the size and the cost, you're like, whoa, it's a very different ballgame versus like a thermostat or a smoke alarm, it's 10 years lifetime. So it's very different ballgame, every single application, every single market. So it's better to understand which market you're going to be focusing on as a sensor manufacturer, and then just see if you can address that exactly what's needed by your end users and customers. And it starts with the dialogue, and you have to reiterate back and forth on that for a while.
Yeah, I would just repeat almost what most of the panelists said. I think the key success for the requirement document to be released to you early is kind of communication and be involved with the end user early on. So if you want to be successful and aligned with their need and meet the requirements, I would suggest that you try to know who your target application is, and you understand who's a player in that domain or that space, talk to them, understand requirements as much as you can, and then you kind of make your material or design or sensor aligned with their application. And then when we talk about requirement is really an application document, right? It comes from the application. So when that document is created, you have in it operation requirement, things that come from the operation environment itself. How long it's going to last and what kind of temperatures needs to survive and the amount of pressure, the amount of vibration and so on. And there is also the voice of customer kind of wish list, right? You have a customer who would tell you, oh, I have a sensor that can meet all the requirements, it does everything I need, but I need to do this thing as well, or additionally measure that thing, or the lifetime being a little bit longer, or it can be seamless in my component, not visible. It doesn't obstruct any airflow and so on. So there are things that kind of, as Joe said, must have, and things called desire to have in your system or your sensor. And understanding both of them is critical for your kind of engagement and success in being a supplier for an end user. Additionally, on the materials are, I would say, the key element in the sensing technology. Every sensor almost has a material in it, and understanding what requirement in the material there is important, because materials are, as you know, can degrade, can change over time, and can respond a lot to the application itself. So,
again, back to the human element for me, and an honest conversation between the user and the developer and the people in between on what is a drop-dead specification, a must-have, and what's a want-to-have. And in my experience, it's also a timeline. In other words, if you ask me, is it possible to develop nano sensors and AI sufficiently to do a lot of multivariate sensing, nanotubes, sampling systems, have the whole integrated package, I would say to you, yes. And there's many people out there are developing different parts of this all the time. And the technology is moving quite rapidly. But if you want this in a package for the field tomorrow, if I told you I could do this, I would probably be overstating it. I don't use the word fib, but I would be overstating. It would be super high risk, if you want to think of it that way. And if you absolutely need it today and need to make an impact, then maybe you have to make compromises. The package is bigger, the power level is higher, you need more sampling, more macroscopic things built around your little nano sensor of today. And so then you look at, well, okay, do I go with a cost of that's undesirable and a size that's undesirable, but I get it quick? Or do I, hold out for everything? And I have a paradigm that says fast, good, and cheap. Pick any two. And if you think about it, it translates really into that kind of world many times. So I want to go on to one more question, or you want to?
No, I just had a short story.
Okay, go ahead.
Users'
We
input.
like stories.
Yeah. So this is actually the sensor that I showed in my presentation about the chemical sensor, and this consortium that funds these projects had a workshop to just define what they want. And so I couldn't go. So I sent one of the young professors there, and he came back and he says, "There's no hope. We're not going to submit anything." I said, "Why?" He said they wanted a sensor that can detect chemicals and that has electronics, and they wanted the size to be between 50 and 70 nanometers. And he said, "That's impossible. We're not going to submit anything." I said, "No, we're going to submit." He says, "No, it cannot be made." I said, "I know it cannot be made." But these guys don't know what they're talking about. So we submitted a proposal, and we proposed something between 100 microns and 500 micron. And guess what? I think our proposal had the smallest size proposed. So that's the case where the user wants something, but they don't really know exactly what they need. And these guys, the reason they wanted 50 to 70 nanometers because they wanted to go in the pores of the rocks to test stuff.
Yeah, so many stories are written in the naked city. So any more questions? I think there was one more out in the audience. No, I have one more. Okay. We talked about nanotechnology and nano materials, integrating them into sensors, and then integrating the sensors into electronics, and then packages and instrumentation or providing information. And the question to the panel is, do self-contained devices provide greater design freedom, greater paths to market than just nanomaterials and sensors? We go right down the line. Whoever wants to.
Yeah.
Yeah, I think this is a really good question and opportunity from N5. Just to give you a little bit of background, so what we are trying to do is take the chemical sensor chip, which is an analog product, and we sell that as a product itself. Combine that with something called ASIC, which is an application-specific integrated circuit, and some other components, put it in a small package with a filter membrane that would, selectively remove some components and particulate matter, everything, in a package, so size of like 3 by 3 millimeter and about 1 millimeter thick. The reason for that is that's the wearables, like, I mentioned before, that's kind of the size, form factor requirement. The reason you're trying to do that is a self-contained sensor is where everybody is going. If you're trying to address the IoT or wearables, industrial IoT, smart homes, this is what you want, because in this day and age, software still makes the products profitable. And as the end of the day, everybody wants data. I mean, nobody really cares about sensors, Like, it can look at a black box, but as long as it provides the data, and people like the app developers and you, on top of that, cloud computing, you add on top of that, and it gives you actionable intelligence that you can do this, and then you can add on top of that, make some services, products, things like that. So putting it all together is a significant challenge, although this is probably the easiest way to get to the market and grow your company rapidly. And you have many examples like that from companies like Sensorion that produces an industry standard temperature and humidity sensor in a single packaged, all digital product. So you drop in any board and it just provides a solution what you need. Anybody with like a, maker type education, like tinkering with like boards, Arduino stuff, they can integrate into their product and actually make a product. That's why you see in the crowdfunding campaign more and more hardware-based products are coming in, because now sensors, if you look at MEMS sensors, everything, this is where they're moving to, all digital solution, like a single package. But there's a problem, is that developing that kind of sensor is extremely challenging and time-consuming and resource-intensive for a startup like our company, because guess what? You have to not only develop the sensor, you have to pay for the ASIC development, you have to pay for the packaging development, you have to line up every single thing. So there are like, kind of both ways, go both ways. That's the easiest way to market, and this is probably what the world needs right now, but it's not the, the easiest to produce and kind of manufacture at a large scale.
But I think, Abhishek, the main point that you really made is if you have the whole package and useful data, like nobody cares about, necessarily the interaction of the sensor and the signal from the sensor, but temperature, humidity, compensated output, then you can go to all of the engineers making products. And this is expensive, and a generic ASIC doesn't exist for all sensors and all sensor types. We have a couple that are coming out for electrochemistry, the TI. They have one now, and they're coming up with the next generation with temperature, humidity on it. And ADI, Analog Devices, is coming out with one. So people are starting to move forward, but until the investment is made, like the investment in semiconductor devices, op-amps, computers, microprocessors, and you see from the 1980s, the first RCA 1802 that we used on our sensor arrays, which had 2K of memory and no I/O at all, to what you can get today for $2 in terms of microprocessors with A to D, with I/O, with temperature, with all kinds of features on them. I think sensors have to be evolutionary, and we have to have platforms that develop that also support the sensor infrastructure in order to connect to the marketplace, to engineers who are doing devices, you know, garage door openers and controls for appliances and all kinds of interesting machines like that. Other comments?
So I would like to make a comment on the question. I would say that the decision whether self-sustained or integrated sensor is an application-driven decision. I would like to point that for aerospace technologies, aerospace components that are really high-end and expensive, some of them could be as expensive as $200,000, $0.2 million worth of a component. What we have been looking into in terms of sensing is to integrate and embed sensors within the component. So those kind of applications require sensors to be just embedded and seamless in existence, that are really causing no harm to your structure design. And the best technology for this is really printing and nano combined together. So you really marry nanomaterials with printing technologies, and this gives you an option to really print things you can't see by eye inside a composite. And that could be a strain gauge, could be RTD, it could be an antenna. And this is part of your manufacturing platform right now. It's not really something that can stand alone or something that can sustain with its electronic readout circuit or front electronic circuit. It's more like you just need to print that design at that specific location with the minimum amount of material or mass added and without any harm to your aero design or structure design, and being able to wire or wirelessly interrogate it in the component. And then that application requires just really a focus on the integration and what kind of manufacturing I need or is available that enables me to print a strain gauge that's kind of 100 micron by 100 micron in size, for example. And that strain gauge is really located to measure the amount of load and amount of damage that could happen during operation of a rotation of a fan blade, right?
Yeah, for me, one of the major things is to have this dialogue, and maybe there can be some instigation of these dialogues by NSF manufacturing, because I think you can play an important role bringing industry and sensor developers together. This whole thing is really part of a very important dialogue that you have to have, because you know you can spend lots of time and money developing a specification or a manufacturing process that's totally irrelevant to a vertical. Yep. And every vertical, whether, you know, Abhishek pointed out automotive, man, these guys are virtually impossible to deal with for small companies. They need 2 supplier manufacturers, assurances, certifications up the wazoo. I mean, it's just crazy. So for a small guy, these are difficult. So it's going to take some partnerships from market verticals to have a discussion around those with sensor manufacturers to integrate these skill sets that are needed to get the nanotechnology to manufacturing to actually verticals. And they're all different, right? Whether you want aerospace, automotive, industrial, biomedical, yeah. Very different. Again, a whole different thing. But some of the major topics in the major market areas could be instigated by NSF. And by the way, I must say that in my experience with NSF, it was one of the few agencies that followed the technology and let the group develop. We had funding for about 4 years from NSF, and now we have a standalone company, and they did that with a lot of the centers. They had initiated funding, and then the centers would have 5 years and then stand alone. And this has proven to be a really successful way to fund technology. And agencies that have unsecured funding and it changes from year to year, and this is not necessarily the problem of the program managers there. They're in a very volatile environment, but they have a much harder time to get some of this mission science done. And I think it would be better if they had core funded efforts that were more secure, because you develop the group, you develop the expertise, you develop the interaction, you develop the supply chain and all the relationships that you need to do a product, which is non-trivial. It takes a long time.
So relatively few of us are probably interested in this. But so my question would be to each of you is there a particular federal program or agency that was really helpful to you in your, those of you in business? And is there a particular federal program or agency that sort of got in the way? But and sure, yeah, no, but I'm curious. I'm interested. No, but I mean, I'm interested in the good and the bad. I'm just curious, but like not long diatribes about paying taxes or something like that.
Sure. Go ahead. You can start. A federal program you like.
So I think a federal program that I would like to point to is the Next Flex Institute. This is a recent manufacturing institute in California, San Jose, funded by the DoD. And the reason we like it, because membership-based, they're trying to bring together industry and academic members, work together. And what was unique about it is that the roadmaps for the project were made by the group, by the institute members. So basically, it's kind of roadmap-driven, and the roadmap is created and made by the members themselves based on their needs and vision for their technologies, right? This is one thing. The second thing is that on their proposals, you need to have kind of team members from different organizations. That requires academic staff as well as industry staff. And they also specify the TRL level for the proposal. So they have a clear description of where in the TRL map they want to make the investment and what technology they want to move forward kind of up into the commercial line. And additionally, they kind of provide feedback during the proposal funding. They provide details on why and why not has been selected and so on. So they're kind of very engaging and cooperative institute.
Yeah, for N5, of course, you all know the SBIR has been, great support, like Angela's program, and then from NASA also. But one program, it's not really a program, but in terms of infrastructure, of course, like from NIST, the CNST NanoFab. And I think NIST was one of the facilities that had this kind of like an architecture which allows like a very easy access for the small businesses to come in with our team of engineers and start building our own like a manufacturing line and R&D line inside the federal facility, of course paying for it. And after that, ARL had the open campus. So I think opening up these really state-of-the-art like the facilities that, of course, taxpayers' dollars went in and building it up, but actually fostering an ecosystem around this local area where small businesses come in and develop a product, and then, of course, get into the manufacturing through contract manufacturers, things like that. And it just helps more small businesses because you see a model that's been, at play, and successfully. We have developed a couple of products working at NIST. So I think that has been a great help for N5. And yeah, it's going on, and we see more and more federal organizations are actually opening up. Not only like, just manufacturing, but also characterization, because that's one thing that small businesses cannot afford, especially, materials characterization. So, that's really helpful.
Okay, so from the standing point of the academia, like the small business startups made out from the university, the NSF Corps is pretty helpful, I would say, and because they provide the program and the courses and they help to bridge the gaps between academia and the industry, and help the faculty to identify the partnership and also the problem and reframe the product development. And that program actually provide a lot of critical questions for you to think about the product development, and that way actually when you stay in academia will think differently, and you can hear different perspective will help you to develop the products. And also I got funding from the USD Nanotechnology program as well, so this is pretty helpful to drive the innovation, to try to have the innovative technology applied to the particular real world problem to solve.
We had good experience with NSF, actually, very good experience. They funded our center, and like Joe said, the long-term funding actually is very, very important, because we would have not been able to develop this technology had we had a 2-year contract, or so that was actually very, very essential. We have not had I'm glad that Sameh had good experience with NextFlex. We have not had that. The concept is very good, but the way that and many of these institutes operates is that the more money you pay, the more say you have in the topic or the call. The more money you pay, the more say you have in which projects get funded. And if you're a university and you can't get your provost to pay the high fee, then you don't have actually much say in what gets decided and so forth. But the concept is excellent, actually. I mean, I just have a little bit of trouble with their fee-based system. There are actually other institutes that do not require as much membership fee, and there are some that require more, actually, membership fees. So that's the only trouble I had. But the concept, actually, I think is very, very good. It's actually more like the Fraunhofer Institute.
I'm in a unique position here since I am government, but we do get our funding from other government agencies, and sustained funding is the key. And my two best sponsors over my career have been NASA and DHS. And those, it's primarily because they had the long-term view and allowed us time to develop the technology and move things forward.
Okay, I think, you know, government programs like government industry partnerships, government university partnerships, and national lab partnerships, I think all of those are part of the technical infrastructure of our country in bringing things forward. I'll tell you one other thing, the Small Business Administration and SBIR. SBIR is really the technical part of SBA, the way I look at it. And the small business have one program, or they have many programs, but one that I used was SCORE, the Service Corps of Retired Executives. My first company, I had an SBIR, and I sold some instruments to Finland. And I said, good God, how do I do this? Import, export, customs, invoicing, and all that. And the Service Corps of Retired Executives at SBA, I called them up, and I said, I need a guy who sold stuff to Finland, you know, and shipped it there. And they found a guy, an ex-executive from Motorola, and he said, hey, you need a freight forwarder. He does all this work. You need a bank and a letter of credit. They do all that work, and it's in and out. It's no problem. And I mean, it was amazingly helpful and interesting at the same time. But there are a lot of programs within SBA that are helpful to technology companies. And the SBIR for startups and innovation is tremendous. And then as you get closer to products, the industry, government relationships are more important. For innovation, I think the government university relationships are much more important. And the national lab system is absolutely a gem in this country and needs to be cherished and resourced more than it is for the mission that we have to fix big problems like our health and climate change and all these sorts of things. And I include the Naval Research Labs and the big labs in with the national labs. They're a tremendous resource for us.
I'm really pleased that you had no complaints at all about the
You have no bad programs, Lloyd, it's clear. but we do have to go for lunch, actually, so if anybody, just I'm afraid we'll run out of time. Oh, sorry.
Very quickly, following up from Lloyd's question, what is your experience with the U.S. patent office?
U.S. patent?
How long, you file a patent, how long does it take to?
They have a small entity filing status that's a little less egregious, but the patent system is still something to navigate unless you've got experience.
We filed more than 100 patents, and on average they take about 4 years, 5 years. Even if it's completely new, those will take 3 years. If it's new, there's nothing like it, for example, it will go fast. But if there's something similar, just even keyword search similar, it will take 5 years at least.
So we really need to break for lunch.
So yeah, I just want people. Arlington is busy, so what I do want to point out to everybody is, I mentioned it before, but this map right here, there are a lot of options around Arlington, so you should be spoiled for choice to eat. And if we can get back here. I think that it's 1:40 is that we'll be convening back. So let's try to do it on time so that we can end the day on time. But that was really a great panel. Thank you so much. I thought that was really terrific. Thank you.